So, good morning, everybody, and welcome to our 19th edition of the Code of the Month. We are happy to have as a speaker today Marta Garcia from BSC Computer Science, and she will talk about some of the tools that COE POP uses to analyze performance of applications. And yeah, I would leave the stage to you, Marta.
Thank you very much. Let me start the presentation. And yeah, thank you very much for the invitation and for the opportunity of talking here. So a bit of introduction of what POP is so that you can understand then which is the role of the tools that I'm presenting. POP is a center of excellence and it's focused on performance optimization and productivity. And we do this by providing free services to any European user or developer. So we offer these services that are about understanding the behavior and the performance of applications and provide suggestions on how to improve the performance of your codes. It's a transversal center of excellence that we provide services to all the different, other center of excellence, NCCs, and in general, European users. So basically in POP, we have two different objectives. On one hand, to provide these assessment services, and on the other hand, developing and evolving the tools and methodology that help us do these assessment services. But instead of seeing it like this, we see it like this, because we do the assessment services, and from there, we see the needs of evolving the tools and methodology. We do the changes in the tools and methodology, and these changes can be applied in the new services where we get, again, new feedback. So this is the way we work inside POP, that we collaborate very closely with the tools development and methodology. So a bit to give you an overview of the kind of services that we provide, the way we work is that we have an online, sorry, one second, Valentin. Sorry. So we have a public form that any customer can request the assessment or the service through the form. Once this form is filled, then we contact the customer and we ask a set of technical questions, which kind of assessment they want. And one of the most important ones is, where do you want your assessment to be done, in which cluster, and who will obtain the traces. Here, the answer can be that they want the assessment to be done in one of the Euro HPC systems that POP has access, and then it will be the POP expert, the one in charge of getting those traces. Or they can say that they want to get the traces in their own cluster. And from there, anyway, we get some traces that one of our analysts will analyze. From that performance assessment, that is the main service of POP, we will provide a report and explain all the findings in a meeting, in a call to the customer. From here, if there are possibility, the customer can ask for a second level service. We provide different kind of second level services: proof of concept, where we do the modifications that we suggested; advisory study, where we analyze any change in the code done by the customer; correctness check on energy efficiency. So now what I will do is I will focus in this part, in the performance assessment. So the analysis of the traces that the analyst does, and which kind of tools we have to do this analysis. And in particular, I will focus on the tools that are developed here at BSC. So we start from, you have a code, you have a cluster, and your simulation or execution that you want to run. When you have everything set up, the main tool that we have is Extae. Extae is used to record a trace of your execution. So it records all the information of what happened during this execution. This is stored in a file that we call a trace, that it's a Paraver file. These files, these traces, can be then passed through a tool that is called basic analysis that will provide us some metrics. So this is an automatic computation of efficiency metrics that tell us which are the main efficiency issues of this execution. These efficiency metrics will tell us where to look when we analyze in detail the trace with Paraver, which is the other flagship tool of the BSC tools. This visualizer will allow us to do the detailed analysis of what we have in that trace. But we have, these are the flagship ones, the main ones, but we have other ones that help us to cover more spectrum of applications and use cases. We have TALP. TALP is a profiler, so you get also from the execution, it records, but it, instead of recording information in a trace, it records only profiling information and provides the same metric that you will be able to obtain through the trace without storing all the data of the trace. So we use TALP for large executions or for production runs. So TALP is meant to be used in production, where you can always get information on which is the efficiency of your execution. If you see a low value in the table, then you know that you need to get a trace for that to do the detailed analysis, but that you don't need to get the trace every time. And we also rely on the NVIDIA Insight systems to get traces of the executions in case that we are running in NVIDIA GPUs. And from there, the data that it's produced by the NVIDIA Insight systems, we have a translator that we call NSys to Paraver that translates the data stored to a Paraver file. This allows us to analyze codes that are not so HPC traditional codes, more AI frameworks, for example, because they don't use the traditional programming models that we are used to analyze with Extae or TALP. And we get all the information from inside, we translate them, and we have the power of Paraver to analyze that information. So later on, I will talk more in detail about these 4 tools, but now let me just summarize a bit the advanced analysis tools that we have at BSC2. So we have the trace. The trace, we have seen that we can analyze it with Paraver, but we also have a simulator that it's called DMMAS. DMMAS gets as input a trace, and then we can change parameters. We can change parameters, for example, the network bandwidth, or we can change the network latency, or we can change the velocity of the processor. So this means that with a given trace, we can produce then a new trace simulating what happens if I'm running in an ideal network where the message arrives instantaneously, or what happens if I run twice the speed, the compute parts of the application. We also have a clustering tool that allows us to do a clustering of the compute burst. This way we can see which burst of compute look the same from the performance point of view, even though from the code maybe it's not so easy to identify them that they are the same kind of computation. And the output is again another trace that includes the cluster ID, and we are able to plot the different clusters in plots like this, or see that in the trace. When we have several traces clusterized, then we can use a tracking tool. This tracking tool allows us to see how the different clusters moved in one of the directions that it could be, for example, IPC or the number of instructions. So these are the advanced analysis tools, but today I'm going to focus only on the ones that I showed before. So the first one is Extae, is the tracing library that it's transparent to the application, platform agnostic. It covers the current version, all these programming models. It also allows to obtain PAPI counters, and it offers the possibility of linking to source through the call stack, the OpenMP routines, or Dynins. All these features don't need to recompile or relink the application, so we can work with the binary as it is and just use a preload mechanism. unless you want to use the API to annotate your code. So sometimes it's useful if you know your code very well, you want to annotate the different parts, and then you will be able to see that in the trace too. To use Extae, as I said, we use the LD preload. We have several libraries depending on what you want to trace. If you want to trace MPI, OpenMP, a combination of both, CUDA, pthreads. So you have several tracing libraries, and you select the one that is useful for your case. And then you configure everything that you want to trace through an XML. Once we have the trace, then we open it with Paraver. Paraver is a data browser that was thought and it's being used for performance data, but we have also used it in different scenarios. So for example, for examining signals of processes in a factory. So it's a very powerful tool because you can configure anything. So you have nothing pre-assumed, and you can compute all the metrics and everything as you want. It has two kind of views, main kind of views, that is the timeline and the histogram, and it allows to load multiple traces. So you can work on several traces at the same time. That allows that to compare them and see differences or where the changes came from. The timelines. The idea of the timelines is to separate the what from the how. So the what is the semantic, and then how is the visual representation of that. So the timeline has this structure. In the x-axis you have the time, and every row represents one object. Objects are applications, processes, or threads, and they are grouped in that at that level. So you have several threads inside one process, several processes inside one application. And then you have different ways of visualizing this. You can have a gradient color for continuous values, and then you have this kind of legend. So for low values, green, high values, blue. And it paints the burst from the color that in the gradient legend. You can also have code colors for the events that are for example, MPI calls. And in this case, every MPI call has a different color, and then you see the coloring. And you can also draw it as a function line where you accumulate, for example, here, how many processes are running in parallel at a given point of time. These are the three main. There are other views, but this is the ones that we use the most. And then we have the histograms. From the histograms are obtained from a timeline, and then it's a way of aggregating the values. Here in the x-axis, in the y-axis, we still have the different objects. So you will have the same here as here, but without the labels. And then in the y-axis, we have the control scale. So it's a way of aggregating the information here in a histogram. And the color tells, you can also define what the color tells you. So if it's the amount of time that it happened in the execution, or the average value of the burst. So everything can be configured. For values that are discrete, like the MPI calls, then you can get this kind of histogram. It's the same, but in this case, we are showing the value instead of only the color. These two are equivalent, but in this one, we see just a pixel with the color, and here we see the value. The next tool that I'm going to talk about is TALP. TALP is a tool to gather efficiency metrics. It's more a profiler than a tracer because it doesn't store all the information of a trace of all the timestamps. And it can work at finalization or at a runtime. If it works at finalization, we just get all the information from the execution, and we print it at the end, and it allows to have a feeling of how your execution is performing. It allows to do continuous performance monitoring, to integrate it with CI/CD, for example. And it can also be used at runtime. So we offer an API, and with asking that API of the punctual efficiency of the execution, we can take decisions at execution. Today, I'm only talking about the when we get all the information at the end, more like a profiling tool. It also provides an API to annotate the regions. And this is very useful because users usually know very well their code. So then they can say, okay, I'm interested in this part, in this region, to separate this region from this region. So we provide this API and then to mark regions. And then at the end, you will get efficiency metrics for separated for those regions. So which is the efficiency of this particular region that you marked with the naming that you provided in the API. And the idea is that it can be used in production runs, and it will tell you when a detailed analysis is needed. So this is not the final point. It will give us the idea, and then if we find that there's an issue with one of the efficiency metrics, then we need to obtain the traces for that. The current version is 3.6.0. Right this week, we will release 3.6.2, and that will be a stable release. And the current version supports all this, the MPI efficiency metrics, hardware counters that we count cycles, instructions, IPC, and frequency, OpenMP efficiency metrics. We also have TALP pages, which is the tool that helps you integrate TALP in CI/CD frameworks, and GPU efficiency metrics that support CUDA, ROCm, and OpenACC. This is so for the very transparent and straightforward use, you will do a LD preload of the TALP library. We will intercept the different calls during the execution and gather all the information. And at the end, you will get an outcome like this one, a text output that tells you the different efficiency. In this case, we have a global region. If you annotate different regions, you will get several reports like this one for each region. And then we have NSYS2PRV. NSYS2PRV came from the need of analyzing other kind of workloads that are not HPC traditional ones, like, for example, AI frameworks. And then we realized that the NVIDIA Insight system already has everything implemented to get all the information of the execution. But the visualizer of NVIDIA is not as powerful as Paraver. So what we do is we translate the information from the NVIDIA Insight system tracing with NSYS2PRV to a Paraver file. And this gives us the opportunity to do the same kind of analysis that we have been doing traditionally to HPC codes to other frameworks, and allows us to go from very detailed insight of what is happening inside of the GPU to how it's performing in large clusters running in several GPUs from the communication point of view, for example. Okay, so this was a very quick overview of the tools, and I went very quick because I wanted to show you a real assessment of which are the kinds of things that we do. So now I'm gonna go over an assessment of a code using TALP, Extae, and Paraver. This was an assessment of a plasma code that was running in more than 7,000 cores, MPI processes, and each MPI process was using 4 OpenMP threads. The first thing that we did with this application, because it was running larger scale and getting a trace of all these processes and the OpenMP threads, was very expensive in terms of the storage and the overhead, was to obtain the TALP metrics. By the customer, we identified that they were interested in the propagate function. So we used the TALP API to annotate the code, and we obtained the metrics for the propagate slice, the propagate function. We see that there's already an issue, a performance issue in this region, and with this information is when we proceed to obtain the Extae trace. as we have now the information of which is the region that we want to focus, that it was the propagate function, we see here the global trace with all the regions annotated by the customer. And we only trace the part that is marked in brown. So the top trace view tells us which part we are tracing. We are tracing just this region of the code. And the bottom trace shows us the function or the region that we are running. And we see that there's an initialization phase, and then the propagate is executed 3 times, and then there's the finalization with the IO. So that's why we say that it makes sense to focus on the propagate region, because it's the iterative one. From here, we zoom in that propagate region, and we see another level of detail of the different regions that it has. We are able to quantify how much time we spend in each one of these regions. And we see that the most important ones are the spatial space, which is this blue, and the propagate fields, which is the this dark red one here. So this top trace shows us the region, and the bottom trace shows us the useful duration. So this is a gradient timeline, and long bursts are shown in blue, short bursts are shown in green, and we see that the black means that there's no computation done here. So usually it means that it's MPI communication. So there's nothing useful being executed when there's black. So now we see that inside the spatial space, we have 3 iterations that look the same, and we will be able to analyze one of them. And we also see that the propagate field is also important, and we will analyze it later. So we focus now on the spatial space. We get again the metrics with TALP, and we see 2 main issues, that it's decreasing the efficiency of this region of the code. The main issues are the MPI load imbalance and the OpenMP serialization. So we will focus in these 2 efficiencies to do the detailed analysis. Now we go back again to the trace, and we do the detailed analysis of the spatial space. We see that it has this structure. There's a lot of point-to-point communications here. There are some long computations in this part, and then there's 2 iterations that has the same kind of pattern but with less data. This is what we can check from this view. Now we zoom in this region marked in red, and we see with drawing the MPI calls with Paraver, we see that the issue is that they are doing a lot of non-blocking sends and receives at the beginning, and then they are doing wait tolls for each one of those calls. But the wait tolls are being done in order, so they are forcing the receiving of those messages in order. So this is one of the messages or the suggestions that we gave the developers, is that you can do a single wait toll for all the calls, and that way you are not forcing the order in which you want to receive the messages. We also are able to compute with Paraver the average bytes transfer, the maximum, the minimum, and the total bytes that are transferred in this region of the code. Now we will zoom in this horizontal. So before we zoom in time, now we will zoom in objects to try to understand what's happening in this region with this load imbalance that we are seeing here. And this is the window that we see when zooming in. And what we see here is, okay, we see that there are different MPI processes, and you see the 4 threads of each MPI process. So here is one MPI process, here another one, here another one. And there are MPI processes with much more work than others. And this can be seen by the histogram of useful instructions. With the histogram of useful instructions, we see that these threads belonging to this MPI process are doing much more instructions than the others. So the load imbalance is coming from an issue of amount of work that each process is allocated. This is some feedback that we also gave to the customer in case they can fix it or do a different distribution of work. And now we go to analyze the propagate fields region, which is the one marked in this part. If we get the TALP metrics for that region, we see that the main issues are the MPI load imbalance here and the OpenMP serialization efficiency. So we check the trace. This is the overall view of the whole region, and we zoom in this part here because it seems to be some load imbalance or some issue because there's a lot of black. So we want to understand what's going on in this part here. When we zoom in this part and then we zoom in only some objects, this is what we see. We see that there are some processes that is doing some work that other processes are not doing. So in this case, this process here is working alone, while the other processes don't have this region, this very long computation burst. And also, the important thing is that this part is not parallelized with OpenMP. So we are not able to use the OpenMP threads to alleviate this load imbalance that is happening at the MPI level. So these are two issues that we detect in this region. One, the MPI load imbalance, some processes having more work than others, and OpenMP threads not being used to parallelize this particular region. Now we focus in this other region that seems to be iterative here. We will zoom in one of these iterations, and then again we will zoom inside to understand what's going on here, because here we see that there are some black holes, so something is not working properly. We will zoom in some processes to try to understand in detail what's happening inside those. So if we zoom in, we see this kind of pattern that it's like an arrow going in that direction. So we could keep zooming in to try to understand where this inefficiency and this arrow shaped is coming from. And we see that there are two different issues in this part, in two parallel regions. In one hand, the green and purple, which are here, these are regions with a load balance at MPI level, because we see this process here executing these long tasks, which are the green and purple, and not the other one. So the other processes are not executing them, only one. So this is producing this delay in this process that is then propagating to the processes that are waiting for him. And these regions, again, are not parallelized with OpenMP. So OpenMP is not helping alleviate this MPI load imbalance. And we have another issue in the blue and red parallel regions. We see here that there are other parallel regions that are blue and red. These are parallelized using OpenMP. And we see that there's a load imbalance at MPI level, because here these processes are executing the red and blue regions, but not this one at the top. This one at the top, the red region, is very small. Is this dot that I don't know if you can see, and these are small dots that you see here. So there's a load imbalance at the MPI level, but we also see a load imbalance at the OpenMP level, because if we look at this zoom here, we see that for here the first the last thread, which is thread number 4 here, is doing more work than the other 3 threads from the same process, and the same in the next execution. So we see that in the blue and red there's a load imbalance issue both at the MPI and at the OpenMP level. So these are some of the analysis that we did for this execution, and some of the feedback and suggestions that we gave back to the developers. And the case that I want to show you now is how we use NSYS to PRV, and sorry, this should say Paraver instead of Extae. and how we use this tool to be able to analyze AI frameworks that don't use MPI, OpenMP, and these common programming models that Extae relies on to obtain the traces. So this is a trace that we obtain with N-side systems that then we translated to with NSys2PRV through a Paraver file, and now we are able to visualize it with Paraver. Here I'm showing two different executions. In this window, you can see the code color is showing you which CUDA kernel is being executed by each GPU. So this is an execution running in 128 GPUs. And here we see a line for every GPU, and the color represents the CUDA kernel that is being executed. And in this case, we wanted to understand the difference of performance doing the same execution. This is a training, a llama training. If we do overlapping of communications or non-overlapping of communications. You would expect the non-overlapping of communications to be slower, because usually you expect to be better to do some overlapping. But the surprise was to see that the execution time was more or less the same. So there's no much difference in the execution time. There is a difference in the efficiencies. So here you can see the efficiencies that are obtained with this execution and the efficiencies that are obtained with this execution. So the GPU parallel efficiency is much lower for the non-overlapping, while for the overlapping, the GPU efficiency is higher. Still, the execution time is the same. How this can happen? Well, what we did is we computed a histogram of a 3D of the duration of the kernels, and here for the top trace and the bottom trace. And what we see is that for the same kernel, so we are selecting one of the kernels here, for the same kernel, you see that the blue bursts are located here are taking longer than the same kernel when executed in non-overlapping mode, that are taking less time, because here the x-axis is the time it takes to execute one kernel, and the color means how many times that kernel is being executed with that duration. So that's why we see here the same kernel is taking longer when overlapping than when non-overlapping. We try to understand better why this is happening, why there are some kernels that perform different, and we get two traces with the difference where we see that the blue here is shorter while the green is longer, and the other way here. So when we try to understand this, what we see is this is when different kernels are being executed in the bottom trace. Here what we see is the number of requests that are being done to the NVLink. And what we see is that if there are several requests being done to the NVLink, in this trace it's happening here, while in this trace it's happening here. This is affecting the duration of the kernel. In this case, as this is happening in this part, it's affecting the green kernel, that it's now taking longer. So what we see is that the communication kernels that are happening in parallel with compute kernels are affecting the performance of the compute kernel, something that we would not expect to happen, that you try to overlap the communication with the computation, and at the end what you end up doing is that you are affecting the speed at which those computations are being done. So this is the kind of information that we can get from one trace obtained with NSys2PRV. And now we had another question. So what happens with the load imbalance? Everybody thinks that in the AI trainings there are no load imbalance, that everything is super well balanced. But this is the kind of view that we get when we zoom in. Again, here we are seeing the CUDA kernels. The color is the CUDA kernels. We compute the load balance, and we see that there's a 77% of load imbalance in this trace. using a profile of the kernel. So now we have a histogram. Every column now is a different kernel, and the blue means how much time the color means how much time each process spends in each one of the kernels. From this profile, what we see is that this kernel here, so the other ones seem to be more or less well balanced, but this kernel here has a load imbalance of 27%. From this, we can filter just showing the durations of this kernel, which is, the name is this very long thing here. This is the kernel from this column, and here is the timeline of the duration of that kernel for the different processes. We can see how there are very different durations depending on the process, and that it has a high variability, and this is producing this load imbalance that we are seeing here. What we see when we check it in several iterations, we check now for this kernel that we have detected here, that is the issue, we come back to the general timeline and we draw it, and we see that the load imbalance pattern, it's repetitive for different iterations. So it's not something that is random, so it's not noise, it's something that keeps happening for every iteration. Now, what happens if we zoom out? Now we zoom out, we were looking inside one of these iterations and we were seeing that the pattern was repetitive. But if we zoom out, we see that this load imbalance is happening now, sometimes in one task, sometimes in another, and it's kind of migrating and changing with every step. So this is also another kind of analysis that we have been able to do with this tool. So to finish, which are the highlights? So POP is providing free services for European users. The idea of these services is to help developers to understand the performance of their codes, to really get suggestions on how to change the code to do a more efficient use of the computational resources. To do this, we rely on a powerful set of tools. This set of tools cover traditional HPC code. So we have Extae that has been developed for several years, Paraver that is a very powerful visualizer tool. And these kind of tools allows us to do this very detailed analysis that I have shown, where we see every microscopic detail of the performance, but also to obtain information at a higher level. To be able also to analyze large traces, large scale executions that nowadays COEs are doing. We also have these other tools that allows us to get the efficiency metrics without gathering all the tracing. With the TALP, we can get these metrics at a higher level and then do the analysis at a microscopic level. And finally, with the NSys2PRB, we are able to analyze other frameworks that are not HPC traditional ones. So giving us this overview of different performance. Our tools are deployed in almost all the Euro HPC systems. And also to share with you that we will have a training on POP3 tools in Mare Nostrum 5 in collaboration with CASTIEL in February in Barcelona. The registration is open, so you can go to the link and get all the information about the agenda, the contents, and the registration link. And of course, you can contact us or request at this email, or directly, if you are interested, request your assessment for your code. So that's thank you very much for listening.